we had been studying unit 1, that is module 1, atomic and molecular structure. So, under atomic and molecular structure, we had taken up the molecular orbital theory, and today we are going to start lecture 4, that is metallic bonding. Of course, I am your teacher Dr. Manisha Shukla from BBD and ITM Lucknow. So, basically we had been studying bonding between two atoms. We would be studying bonding between two atoms. Now, today what we are going to take up is that how do so many atoms in a metal stay together? Now, how are they held together? Till date we were taking up two atoms and we were studying their bonding. So, now we will be in today's lecture we will be studying metallic bonding. We will be studying metallic bond on the basis of M.O.T. Of course, there are many theories proposed for the metallic bonding, but that will be our focus, the band theory or the M.O.T. Then bonding in lithium metal. So, as per M.O.T, how do we explain bonding in case of lithium metal? Then we will be taking up of course classification of solid on the basis of band theory, then comparison between conductor, semiconductor and insulators, and some of the properties of the metal which are very well and beautifully explained on the basis of band theory of metallic bonding. So, definitely we will first take up what is metallic bonding, how do we define metallic bonding, then of course a vague idea about the various theories of metallic bonding, and finally the band theory or the molecular orbital theory of metallic bonding. So, how do we define metallic bonding? So, the force of attraction that holds the metal ions and the free electrons within its sphere of influence is known as metallic bonding. So, as we know that metals tend to lose electrons very easily. So, therefore, you can say that by gain of a little amount of energy, the electrons move around the metal and the metal left behind or the atom left behind has a sort of a positive charge, which we term as kernel when we study the electron C model of metallic bonding. So, it is the bonding between atoms within the metal, that is the bonding that holds atoms in a metal together due to the electromagnetic interaction between the electrons and the rest of the atom, and that is a kernel. Such bonds are collective in nature, it is not a bond between two atoms. So, metals have innumerable large number of atoms. So, a bonding between all those atoms, okay, accounting for many of the, and such kind of a bonding accounts for many of the physical characteristics of the metal, and whereas the chemical bonds if you think of are localized between neighboring atoms only. So, chemical bonds which we have been studying till now, अभी तक जो हमने केमिकल बॉन्डिंग पढ़ी है जैसे आयनिक बॉन्डिंग, कोवलेंट बॉन्डिंग, कोऑर्डिनेट बॉन्डिंग, वहाँ पर हम दो एटम्स के बीच की ही बात करते थे और उनके बीच जिस प्रकार की बॉन्डिंग होती है उसका डिस्कशन करते थे. जब हम मेटल्स के बारे में सोचते हैं तो बहुत सारे एटम्स होते हैं, लेट्स से in the order of 10 to the power 3, multiples of 10 to the power 3. So many atoms are held together. It is a matter of definitely study, curiosity and research that how so many atoms are held together, they do not move around and they still show specific properties which metals do exhibit all the time. So, the various theories of metallic bondings which have been proposed for so long, one of the very popular theory as we discussed in case of normal bonding, bonding between the two atoms, that is of course, there also we studied a bit of valence bond theory, of course VBT, but then VBT since was more confined to two atoms or for just a few set of atoms it could be explained. Therefore, this particular theory was not a very popular theory, it had its own drawbacks, anomalies. Then came the electron C model, which of course was much more successful compared to valence bond theory. So, in case of electron C model, it was proposed that the kernels, if we can write it as the kernels are embedded in a pool of or a sea of electrons. So, it was assumed to be something like this. There are plenty of kernels. That means atoms which have lost their electrons, or the electrons are somewhere around them, not really closely associated to them. So, this was again another proposal which became very popular and which could explain large number of properties, except for a few, like some of the properties, like why sodium is so soft in nature, right, whereas osmium is so hard, why gallium or mercury is a liquid, whereas the other metals are solid. So, such kind of discrepancies, the anomalies, could not very well be explained by electron-C model. Though electron-C model was near to perfection, it could explain large number of things regarding or in comparison to the valence bond theory. Of course, valence bond theory was associated with very many drawbacks, like the valence bond theory could not explain electrical and thermal conductivity even, and it could not explain the metallic luster also, but electron-C model could explain many of the properties of the metal, but still it was left behind with some of the drawbacks, mainly, as I said, mercury having a very low melting point like nearly minus 39 degrees Celsius, while tungsten having such a high melting point like somewhere around 3300 degrees Celsius, and sodium and potassium are so soft that it can be cut with knife, while osmium is so very hard, and with rise in temperature the electrical conductivity reduces, and this particular fact also could not be very well justified in case of electron-C model. So, there came another concept. By then, of course, the molecular orbital theory had become very popular. तब तक molecular orbital theory, the quantum mechanical approach of explaining molecules, बहुत अधिक विस्तृत तरीके से जाना जाने लगा था, उस पर बहुत सारी रिसर्चेस होने लगी थी. तो अब बात हुई कि मेटल्स की बॉन्डिंग को भी हम MOT के आधार पर एक्सप्लेन करें, और इस प्रकार के एक्सप्लेनेशन में से अराइज हुआ हमारा द बैंड थ्योरी ऑफ मेटालिक बॉन्डिंग. नाउ अकॉर्डिंग टू दिस थ्योरी, the electrons in the metal are considered to cover the whole crystal lattice and are not localized between any two atoms only. Now, this can very well be understood, because in case of metals, the moment a little bit of energy is given, even energy from the visible radiation, these electrons very easily move out of their premises. And then metallic bonds are formed by delocalization of all the orbitals containing free electrons. Then, according to M.O.T, when two atomic orbitals combine, two molecular orbitals are formed. This we have been studying earlier also, which we called the law of conservation of electronic state. Now, the same follows here also, but in case of metals, now when two atomic orbitals combine, they form a BMO and an ABMO, bonding and an anti-bonding MO. But if three atoms combine together, three atomic orbitals combine together, they form bonding MO, they form non-bonding MO, and they form anti-bonding MO. So, therefore, again the concept of conservation of electronic state is followed over here also. Similarly, when n atomic orbitals combine, n molecular orbitals are formed. तो उसी प्रकार से जब n atomic orbitals एक साथ मिलते हैं तो n molecular orbitals generate होते हैं. In case of metals, n is of the order of, as I said, Avogadro's number 10 to the power 23. So, 10 to the power 23 molecular orbitals of that order will be formed. They are closely spaced, forming a continuum, because they are very closely spaced. So, it appears as if it is a continuous band of energy, and this continuous energy band, of course, that is why, because of this continuum, the theory is known as band theory. So, why is it called a band theory? Because of the closely spaced energy levels, which are so closely packed that they appear like a band, and that is why this theory, or the molecular orbital theory of metallic bonding, is known as band theory. So, now let us take up an example, lithium. Let us take up lithium as an example and try to see how these bands are generated and how we explain bonding in lithium metal. So, lithium, as you know, has 3 electrons, can be distributed as 1s2, 2s1. So, we will be considering the 2s1 for bonding over here. So, when the 2 lithium atoms combine together, the 3 lithium atoms combining together, 4, 5 and n number of them. So, let us see. Now, have a look over here. Have a look over here. So, the band theory for lithium lithium says that MO is produced by linear combination of 2s orbitals in Li2, Li3, Li4. They are represented over here. Let us have a look. Note that for every atom added, an additional MO is formed. The energies of the MOs get closer together. So, when a sample contains a very large number of lithium atoms, as I said, Avogadro's number के order में होता है. Okay, so the states formed are so close in energy that they form a continuum. They form a continuum, as it can be seen over here, and this is known as band of energy, and thus the band theory. Now, let us have a look. 2 lithium atoms over here. So, one BMO and one ABMO. So, this is BMO and this is ABMO. Okay, the electron pair would be occupied in the BMO and the ABMO will be empty. When 3 lithium atoms combine together, these were the 2 lithium atoms combining together. When 3 lithium atoms combine together, so you have 3 lithium atoms over here. So, when you have the BMO, you have the ABMO on top, and this is the non-bonding, this is the, so this, the middle one is known as the non-bonding MO. Okay, this is ABMO and this is BMO, and in between is the non-bonding MO. In the similar manner, large number of atoms go on combining together, and therefore, a continuum of energy closely spaced. BMOs are there and the ABMOs are all vacant. Okay? And if there is an odd atom, then in that case a non-bonding MO would be there, which will appear as a overlapping region, and therefore the electrons won't have much of a gap, energy gap between the BMO and the ABMO, and hence they will be able to jump across to the conduction band from the valence band with a lot of ease. Okay? So, now application of band theory in solids. Let us have a look at the application of band theory in solids. Formation of conductors, semiconductors and insulators on the basis of band theory of solids. Quite important, and in exam also this is very popularly asked. So, all the children, please pay a lot of attention to what is being said over here, what is being talked about over here. So, formation of so with the help of band theory we can classify solids into conductors, semiconductors and insulators. So, these are, we can classify them into conductors, semiconductors and insulators. So, the outermost completely filled or partially filled energy band is known as the valence band. So, here is your valence band, partially filled or fully filled. The band above the valence band, which is empty, okay, at 0 Kelvin is known as the conduction band. Now, this is your conduction band, and the energy gap between the valence and the conduction band is known as, either you can call it energy gap, you can call it band gap, and you can also call it forbidden gap. So, these bands are important from the conductivity point of view. Why? Because you know, now have a look at why is it important and how do we classify materials as conductors, semiconductors and insulators. Now, it is the band gap, it is the energy gap between the valence band and the conduction band that decides whether a material is going to be a good conductor of electricity, or it's going to be a semiconductor, or it is going to be an insulator. Now, you can very well have a look at the diagram. Meanwhile, materials are classified into 3 categories depending on the width of the forbidden energy gap. So, what was forbidden energy gap? The energy difference between the valence band and the conduction band. So, that is known as forbidden energy gap. Okay. Now, let us have a look for the conductors. Okay. Now, for the conductors, now valence band and the conduction band are overlapping. As we had seen earlier, you can have a look at the previous slide. Over here in case of lithium, over here in case of lithium. Now, let us have a look in case of lithium. Now, in case of lithium, as we were seeing that in between, when we have an odd atom, therein a non-bonding orbital appears which has an electron in it, which acts as an interlink between the valence and the conduction band. So, therefore, the electron very easily steps up, moves on to, it's an overlaps. Okay. So, that is what I am saying. So, let us have a look at the conductors. So, what are conductors? Conductors, in conductors there is no forbidden gap between the valence band and the conduction band. It can be seen over here. So, there is no gap between the two. The two bands overlap, and hence even at room temperature a large number of electrons are available for conduction, for example iron. So, the electrons do not need much effort. So, they just move on to the conduction band effortlessly, and hence metals are very good conductors of electricity. Now, let us have a look at the insulators, or as you can see in the diagram over here, insulators are the ones which have large energy gap, and because of this large energy gap, the electrons cannot easily jump from the valence band to the conduction band, and therefore no flow of electric current. As we know, electric current or the conductivity is nothing but the flow of electrons. Whichever direction the electron flows in, the current flows in the opposite direction. So, therefore, let us define the insulators. In case of insulators, there exists a large energy gap between the conduction band and the valence band, and that is of the order greater than 9 electron volts. Okay. So, it is impossible for electrons to jump from valence band to the conduction band. Hence, such materials cannot conduct electricity and are called insulators. For example, diamond, glass, wood, mica, paper, etc. Okay. Now, let us have a look at the semiconductors. Now, as I said, look at the diagram for the semiconductors. Here are the semiconductors. In case of semiconductors, the energy gap is there, but not that large, of the order of approximately 1 electron volt. So, therefore, if a little energy is supplied, these electrons can easily jump to the conduction band. Or semiconductors are normally of two types. So, whenever there is some kind of an impurity added to it, that also facilitates the flow of electron from valence band to the conduction band by providing an impurity band in between. So, semiconductors are neither insulators nor conductors. The energy gap is in such materials is between conductors and insulators, and that is of the order of approximately 1 electron volt. Okay. So, such materials are called semiconductors. For such materials, the energy provided by the heat at room temperature can lift the electrons from the valence band to the conduction band, and therefore, at room temperature semiconductors are capable of conduction of electricity, but at 0 Kelvin or absolute 0, all the electrons of the semiconductor material find themselves locked in the valence band itself, and they do not conduct electricity at absolute 0. Okay. So, hence at 0 Kelvin, the semiconductor material behaves like a perfect insulator. Okay. So, as I said, semiconductors are of two types, the intrinsic semiconductor and the extrinsic semiconductor. Okay. So, intrinsic semiconductors, and intrinsic semiconductor is the semiconductor in its pure state, that is no impurity is added to it, no doping. Okay. So, for every electron that jumps to the conduction band will generate a hole, and that can move freely in the valence band. The number of holes are equal to the number of electrons that have jumped to the conduction band. So, such semiconductors are known as intrinsic semiconductors. Then what are extrinsic semiconductors? Extrinsic semiconductors, as I said a little earlier, are the ones in which some kind of an impurity is added, and that impurity generates an impurity band and also facilitates the conduction of electric current. So, extrinsic semiconductors, in extrinsic semiconductors an impurity is present, due to which, due to this impurity, an impurity band appears between the valence and the conduction band, and this is called, the concept is known as doping. Okay. And what kind of doping can take place? Semiconductors therefore are of two types. P type, if trivalent doping is there, then they are P type, and N type if pentavalent doping is there. Now, trivalent, if we have trivalent doping, then in that case, for trivalent doping will be deficient of one electron. So, generating a kind of a positive effect, P type. In a pentavalent doping, it will have an excess electron compared to either silicon type of semiconductor. So, therefore, an extra electron will be present, and that will lead to the formation of a N type semiconductor. Okay. So, comparison between conductors, semiconductors and insulators. Let us compare. Fine. So, conductors, semiconductors and insulators. Of course, in case of conductor, they easily conduct electric current. In case of semiconductor, the current is conducted, but it is lesser than the conductors, greater, of course, much greater than the insulators, but it does conduct. Okay. Insulators do not conduct any current at all. Then conductors, they have one valence electron in its outermost orbit. In case of semiconductor, has 4 valence electrons in its outermost orbit, and in case of insulators it has 8, the octet may be complete. Then conductors are formed using metallic bonding, semiconductors are formed due to covalent bonding, insulators are formed due to ionic bonding. That is the most popular concept. Then valence and conduction bands are overlapping in case of conductors. Valence and conduction bands are separate, but a very minimal energy gap is there of approximately 1 electron volt. But in case of insulators, the energy gap is so much so that it is of the order of 6 to 10 electron volt, or approximately 9 electron volt or above. Then in case of conductors, resistance is very small. In case of semiconductors, resistance is high, and then resistance is very high in case of insulators. Now, it has a positive temperature coefficient, it has a negative temperature coefficient, and it has a negative temperature coefficient. For example, for conductors, copper and aluminum are good conductors, silicon and germanium are semiconductors, as we know, mica, paper, etc., they are insulators. We have been studying them for quite some time and we know them also. Okay. So, therefore, the other properties of metals, the other properties like metallic luster, and these properties, children, are important because in exam, in the short answer form, these properties may be asked to justify. So, what is metallic luster? So, in metallic luster, all the metals are shiny, you know that, because when light falls on the surface of the metal, the loosely held electrons or the free electrons absorb photons of energy, move to the excited state, falling back they give out the same energy, and all kinds of wavelengths are emitted out, and it appears like a shiny surface. It appears like that. Okay. Then thermal conductivity. When a part of metal is heated, the kinetic energy of the electron in that region increases. Now, you can imagine it like this. This is a metal slab and it is being heated from this end. So, these electrons get energy, then they collide with the other electrons and pass on the energy via collision, and the other part also gets heated up. The other part also gets heated up. Then we have the electrical conductivity. Okay. So this is how you can explain thermal conductivity. Okay, making metals in this way, the heat travels from the hotter to the cooler part of the metal, making them good conductors of heat. Electrical conductivity. Metals conduct electricity due to presence of free and mobile electrons in them. So this is what we have been discussing all this time, that electrons, the free and mobile, the delocalized electrons from the valence band, they move on to the conduction band with ease, with a little energy, they just jump there, and there they are free to flow across. So the moment you apply potential difference across a metal sheet, these free electrons move through the circuit and help in conduction of electricity. So metals conduct electricity due to the presence of free mobile electrons, the absence of electric field. The free electrons in the metal lattice show random movement there itself and do not conduct. So, but the presence of electric field, the electrons get channelized in a particular direction, and therefore they very move towards the anode, and thus they conduct electricity. So this is how metals become good conductors. Now another point that is important and is asked as a question, that in case of metals, by rise in temperature, by heating it up, the conductivity decreases. So you have to give a justification to that. Now how do we justify that particular concept? Now the justification is because the vibrating kernels, like the electron has, see, this is the metal. Okay, so in a metal, the electron is easily separable from it, and this is known as kernel. Okay, so now when this electron, when you heat it up, so these electrons move fast and the kernels also start vibrating fast. So when these kernels start vibrating fast, they hinder the flow of electrons. They come into the passage of flow of electrons, and the more you heat, the more is the movement in kernels, and therefore the more they hinder the flow of electrons, and hence with rise in temperature the electrical conductivity decreases, and this is an explanation, please remember it. Metals are malleable and ductile. What does the word malleable mean? Beaten into sheets. And what does the word ductile means? Drawn into wires. Okay. So due to the non-directional nature of metallic bonds, the layers of atoms can slide over each other easily when force is applied, and hence only the shape of the metal or the crystal changes into sheet or wire. So this is how we explain malleability and ductility. Malleability and ductility can easily be explained with the help of electron C model also, wherein when you hammer it nicely, the interspace between the kernels increases and the kernels roll into in between, spreading it into sheets or drawing it into wires very easily. Okay. So if you stretch it nicely, it can be drawn into wires, and ऊपर वाले जो एटम्स होते हैं वो बीच में उसके आके एडजस्ट हो जाते हैं, और जब शीट से हम हैमर करते हैं तो वो फ्लैट उसको बीच बीच में आके एडजस्ट होते रहते हैं और एक फ्लैट शीट के फॉर्म में हम उसे ड्रॉ कर सकते हैं. सो दिस इज हाउ वी एक्सप्लेन malleability and ductility, right? So these two important points are quite important. Malleability and ductility concept is also important. Question regarding why with the rise in temperature, conductivity reduces. So this was our class regarding metallic bonding. Thank you so much. I hope you will go through it very nicely and you will revisit it and learn it. Thank you for attending my class. This is Dr. Manisha Shukla.